So last time we used the raising and lowering operators to go through and find out a lot about our angular momentum eigenstates. So now we're going to take a different approach and hopefully learn a lot more and connect back to a lot of the things we've been doing with three-dimensional quantum mechanics. So we're going to go back and start with our definition, classical definition of angular momentum, L equals R cross P, and put in our three-dimensional quantum mechanical momentum, negative IH bar times the gradient. And here I just sort of organize things a little bit. So what we want to do is to start out is we want to actually figure out this cross product here. And we're going to do that in the most advantageous coordinates we have, which are the spherical coordinates. Again, you can go back. I have a rather lengthy video talking about spherical coordinates if you're interested. But what we want to do is actually go through and do this cross product. So let's draw my spherical coordinates. And so I'm actually just trying to sort of represent this. This is a tricky part, and I know when I was doing this, I wasn't super set on how this worked. And so let's actually draw our R vector in. So this here, it would be our Z, Y, and X. Those are our Cartesian guys. And so let's imagine this vector is in the YZ plane. Okay, and so if I'm going to write out my coordinate system in spherical coordinates, my r hat would be in the direction of the radius there. Now this is increasing theta, and so my my theta hat vector would go that way there. And then the way I've drawn this picture here, so this would be my phi going like that. And so the vector in terms of the increasing phi would be pointing into the page kind of like that there. So I really want you to stop and make sure this picture makes sense. Okay, I know that when I was first learning this stuff, this is pretty tricky to visualize this. So I want to make sure that everybody can get that. So take some time looking at that. And of course, remember that as I move that r vector around, so I have it in that zy plane. As I move it around, they'll stay orthogonal to each other, but they're going to go in different directions, right? That's what's kind of tricky about this coordinate system. So if I rewrite this over here as such, then what I want to do again is to try to do this cross product. And so I can write my r vector as the length r times r hat. And then what I want to do is just kind of, you can do this different ways, but I think this is a nice quick way to do it. Is I can look here at just, as I do this cross product, I'm going to be basically taking the r hat vector and crossing it with the three different directions. And of course, whenever I take r cross r, I'm going to get 0. And so now in this picture here, so we're just going back to doing cross products. So you're going to do your right hand rule. I'm just going to actually have you do that. So if I go r cross with theta, all right, you should get something pointing in the phi direction. And then if I do r cross phi, so r cross phi, I end up pointing in the negative theta direction. Okay, so once we realize how these three unit vectors cross product with each other, then we can write out our angular momentum. This is sort of the whole beastly thing here. And so it's negative IH bar, and I'm just basically going to take the cross product of the r vector, which we're writing as the magnitude r times r hat, times the three different pieces here in the gradient. And we just go through and do these individually. And so negative IH bar. So here we know that r cross r is just 0, so we forget about that piece. Here, what's nice in both these last two terms, the magnitude just cancels out. So we clean that up a little bit. R cross theta hat will be phi hat. And then the only thing that remains there is a d theta. And over here, r cross phi is negative theta hat. And then we have left over 1 over sine theta. And so this is our angular momentum vector written out in spherical coordinates. Now it's going to be more convenient for us to write this in terms of our Cartesian unit vectors, because we're going to be interested in the angular momentum in the x, the y, and the z direction. And so we go back to these definitions. Again, if you go back to my video on spherical coordinates, we describe this. This is how you can write the Cartesian coordinates, or actually the spherical coordinates in terms of the Cartesian coordinates. So I'm literally just going to take this guy and plug it in there, and then this guy and plug it in over there. And when you do that, make sure you go through and do this, and you get the setup looking like this here. So you have your 3, the L in the X, L in the Y, and L in the Z. And of course, the L in the Z comes out fairly simpler. Again, that's because we sort of started with that as our preferred axis. And so now we have the functional forms of our angular momentum, and so we can start going forward and try to figure out the functional form of our angular momentum eigenstates. So we found the functional form of LZ, and so now what we want to do is find the functional form of L squared. These are our compatible observables, and so this will be helpful for us. And so different ways to do that. I'm going to pick the way to take the version of the L operator in spherical coordinates and dot it with itself. Now, here's what I get when we do that. So this isn't quite as simple as what you would expect for a dot product. So let's go through this slowly for instance. So first of all, there's this factor of negative IH bar squared, which is just negative H bar squared. So let's just put that outside and forget about it. Now let's look at this piece here dotted with this piece here. So you have phi hat dd theta dotted with this term phi hat dd theta. And so there's going to be two terms that you get from that. You get the first term would be taking the derivative in over here, and so you get phi dot phi, second derivative. That would be the sort of typical term you would think about. Now the fact is here the spherical coordinates depend on the actual angles. Okay, so you can't just you got to actually do a product rule here. And so then what I would have, I'd have something kind of like this. So I did the first one, I took the derivative of the second part, so now I'd have phi, and I'll say dotted with dd theta times the function phi, and then times an extra factor of dd theta. So we've actually got to explore, okay, let me just write this a little bit more clear, this here. And so if you look at these two pieces, this is just one, of course, these are unit vectors, and so this term would be over here, and then this term here, let's see, I wrote it right over here. And so it's phi dotted with the derivative with respect to theta of phi. Now, if I take this term dotted with this term, it'll be the similar picture. I'll get this piece here when you just end up with the theta hat dot theta hat. But then the other piece that I'll get is theta hat dotted with dd phi of theta hat. Again, because your unit vectors and spherical coordinates depend on these angles. And then finally, these would be our cross terms, which again, typically with a dot product, phi and theta are orthogonal, but phi is not necessarily orthogonal with the derivative with respect to theta of theta hat. And so we've got to explore these pieces a little bit more. So let's do that. All right, so how do we determine exactly how these unit vectors depend on the angular coordinates? And so the way we do that is we take these relationships here. Again, if you go back to the video I have rather lengthy on spherical coordinates, we sort of justify these equations of relating the spherical coordinates to the Cartesian coordinates. And so that's one nice way to do this here. And so what I can do here is okay, so I take the derivative with respect to phi of theta hat. So this is theta hat right here. So if I take the derivative with respect to phi, so first of all, from this term, I'll get just the cosine theta that doesn't depend on phi. And then this cosine turns into a negative sign. So I get that piece there. And then over here, I get y hat, again cosine theta, and this sine turns straight up into a cosine. This piece here does not depend on phi, and so we come out with this right here. And what I can do is I can kind of just sort of play around with this, and so say cosine theta, and then this equals negative x hat sine of phi plus y hat cosine of phi. So it actually ends up being this guy here. And so from this, I can write d phi theta hat is equal to phi hat times cosine theta. Now I won't do all of these for you, but you can go through and just make sure you convince yourself that these are true. But I can write these guys out here, and there's basically a whole bunch. You can sort of do any permutation of these here. So go at it. Make sure you can prove these to yourself. But now we're going to take these back and look at our expression. So here's our really ugly expression. Now these two pieces, we've already done the dot product, so we like those. We're going to keep those. And so now we just want to see how these derivatives are going to work out over here. And so let's look at this first one. So you can show yourself that d theta of phi hat is 0. And so if I go over to here, then that means that this guy right here just goes to 0. So that's nice. Now d theta of theta hat is negative r. So I find that one over here, d theta of theta hat. And so this will be the vector r. Well, we know that if I dot phi dot r, that's just 0 too. So that piece is 0. And then this one over here, d phi of theta hat is again phi hat times cosine theta. So we don't care too much about the cosine theta, but we can just stick it in there anyway. So phi hat cosine theta, and again theta hat dotted with phi hat. Once you see this derivative is 0. So basically these three pieces come out to be 0. This one is going to be a little bit more interesting. And so let's look at that one. And so again, I advise you to go through and do these derivatives, but I got d phi of phi hat is this right here. And so if I write out this L squared piece, I get negative h bar squared, the second derivative of theta squared. So these are the first two pieces that we've already done the dot products. We like those pieces. And so right here, this piece will be negative r hat sine theta plus theta hat cosine theta. And so I'm dotting that with theta hat. And so this is going to be the piece that's interesting to me. So this piece, when I dot it with theta hat, will just be 0. And so what happens is these two negative signs will cancel, so I get plus, and then it'll end up being theta hat dot theta hat, which is just 1. And so I'll come up with this term cosine theta over sine theta d theta. And so let's take this and explore this a little bit. So now what I want to do is you'll typically see this written this way here, just a little bit sneakily, basically in a more compact form. Pardon me. This is 1 over sine theta. And then derivative with respect to theta of sine theta d theta. And you might even recognize this. Right. And so here's, again, this is the way we can express L squared in terms of our spherical coordinates, the functional form of L squared. And we're going to see that this then turns out to be our angular equation from previous discussions on three-dimensional space and quantum mechanics. Okay, so we're getting close to being done with most of our theoretical side of angular momentum. So we've been able to go through here and figure out the functional form of L squared and the three components Lx, Ly, and Lz. And so here's L squared. Hopefully you can follow how we got here. Okay, please go back and double check and make sure you get it. But what we can do now is go back something we looked at before, the angular equation. So here's our angular equation. We wrote it kind of in a funny way like this. But let's go ahead and take this sine squared. Let's just take this whole equation and multiply it by 1 over sine squared theta. So if I do that, I end up with this here, 1 over sine theta d theta. Now I'm going to take what I called y. Remember, these y's are the spherical harmonics, and sort of pull it out here. And so see if you follow what I'm doing. So that guy, and then here, because we're multiplying by 1 over sine squared, I introduce 1 over sine squared theta here with this second derivative of this guy. So let's just put parentheses around this thing. And so here we called this y. Now when I multiply sine squared over to this piece, it's just going to cancel out this guy completely. And so I get this L plus 1 like so. times that. Okay, so I write this out here. Now if we just go back, hopefully you can see that the thing I just wrote out is exactly the same functional form as this thing over here. And so if I take this now and say multiply by negative h bar squared on both sides, okay, so over here I'll have to clean it up a little bit. So I get rid of that negative sign over here, and I get h bar squared this. And so this is exactly the equation we got before when we were doing the raising and lowering operators. And so what this says here is that we've already solved this equation. Okay, this is the same eigenvalue equation we just looked at, and we solved this. We solved the functional form of this, looking at it like a differential equation when we solved the angular equation back a little while ago. And so, and essentially the important point here is that we're getting is that the angular momentum eigenfunctions are the spherical harmonics. All right, and so we just sort of got done talking about how our angular momentum pieces have two quantum numbers, L and M. Well, we already were using those when we were discussing the spherical harmonics. And so hopefully we're able to, in our minds, connect essentially everything we've been doing now in three-dimensional quantum mechanics. One last thing we can do is if I go over here, so this again is our angular equation. Way back, in the day, we described this is our functional form of these spherical harmonics. And so now we can take our new LZ operator and attack it on one of these guys. And so our LZ operator, just look back a little bit in this video, was this here. If I look at this form, the only thing that has a phi is this little exponential piece here. And so if I attack this operator onto that function, right, it's going to leave me from here, the derivative of that exponential will give me an I times m. And basically everything else in that function will stay the same. And so negative I times I is just positive, and we get our other eigenvalue equation. So again, what we've found here is, so we originally did this by going through and finding the eigenfunctions of the Hamiltonian. Well, sort of by doing this, we found the eigenfunctions of L squared and LZ. And so these are the eigenfunctions both of our Hamiltonian, or I guess just to be careful, they're the angular part of the Hamiltonian in our angular equation, but they're also the eigenvalues of angular momentum. And so we're going to spend a lot of time in this course, and actually in the next course, untangling this and really understanding angular momentum, which in a sense is a really important component of understanding three-dimensional quantum mechanics. And just one thing real quick, it's a subtle point, you may have missed it, we're going to keep harping on this, but the functional forms, okay, this angular equation does not allow angular momentum of values of a half, right? When we did this, the angular form of L, right, so only allowed integer angular momentums. We could have like L equals to 1, L equals to 0, L equals to 2, something like that. Well, the raising and lowering operator left open this possibility of fractional forms. Okay, we're going to find that we're going to use that for spin. And so just to kind of get you ready for that, and so we'll find that orbital angular momentum will have to be integer. Okay, that orbital quantum number will be integer, whereas for spin it can be multiples of a half.